All right, so today we're going to cover Chapter 8. And for us to get through Chapter 8, we got to make sure, I'm assuming everything's okay with Chapter 7. So if Chapter 7, if you got issues or if you're shaky on Chapter 7, now's the time to raise your hand and ask some questions. Because Chapter 8, we're gonna get deep into this material and go from there. Okay, so just to recap, in Chapter 7 we learned about a sampling distribution. Now, does anyone want to tell me what a sampling distribution is? Yes?
Sampling distribution is a random sample taken from a bigger population.
Okay. The sampling distribution itself is not a random sample taken from a bigger population, but it's built by taking random samples from a population. So again, the idea is we've got a population. I think last class we talked about a giant vat of M&M candies, and we said, 15% of these M&Ms are blue or something like that in the vat. So 15% are blue, and then if I take a random sample out, we can ask what's the probability that my sample has 18% or more blue or something like that. This is a familiar concept, right? So if I were to suddenly put this on a quiz or test and said you're going to take a sample of 60 pieces, and I'm asking what's the probability that you have 18% or more blue, you guys could answer me.
Yeah.
Is that correct? Okay. And so the sampling distribution is the distribution of the p-hats. P-hats follow a normal distribution. This is the sampling distribution. And what is the mean of this normal distribution? It's not 0.
0.15.
0.15. Okay? So if the population is 15% blue, every time I take a random sample, I'm expecting something around 15% blue. Sometimes it'll be more, sometimes it'll be less. And what's the standard deviation going to be?
Standard error.
Okay, the standard error, what's that?
Square root.
Square root of, okay, yeah, so, not p hat, but p times 1 minus p
Over n.
over n. So in this case, 60. Okay, great. And then so now we have the normal distribution, which is our sampling distribution, and we can answer what's the probability that we get 18% or more blue. Okay, that's what we did in Chapter 7. Now in Chapter 8, we are going to use our understanding of sampling distributions and the fact that whenever I take random samples, that p hat comes from a normal distribution. We're going to use this understanding to help us make conclusions or statements about the population. So in Chapter 7 we said we knew what the population looked like, and because we know what the population looks like, we have an idea of what a random sample should look like. Now we're using the opposite process. Now I have no idea what the population looks like. So just imagine I've got a giant vat of M&Ms right here, and I said, you know what? Somebody mixed up my M&Ms. I'm so angry, and they changed the proportion of blue M&Ms. I have no idea what proportion of blue M&Ms are in this giant bucket now. Okay? And I don't feel like counting them all. Actually, this bucket is so big, there's no way I can count them all. But I can shake it up, and I can take out a sample. So let's say I stir up the giant bucket, and I pull out a bowl of M&Ms, and I count what percentage is blue. So I dump out, let's say 100 M&Ms, and let's say 20% of my sample is blue. I still have no idea what proportion is in the bucket, or is in the giant vat. But I do know that in my bowl of 100 M&Ms, 20% are blue. So, do you think the percentage of M&Ms is now higher than 15%, or could it still be 15%? Do we have any idea what proportion is blue in the giant vat?
Oh.
No? Yes? Okay, so my bowl of 100 M&Ms has 20 blue M&Ms, so 20% is in my bowl. But in my giant vat, I have no idea, okay? Or do we have an idea? We have an idea, right? A little bit, right? Because if somebody said, oh, you got 20% in your bowl, there's probably 90% blue in the bucket. You'd say, that's ridiculous, right? There's probably not 90% blue in this giant bucket. If somebody said, it's only 1% blue in the giant bucket, you would also say, that doesn't quite sound right. So what would be reasonable guesses for what could be in the giant bucket? Yeah?
If your sample of 100 is truly random, then you could say that it's also 20%.
Okay, so if our sample is truly random, and I got 20% in my sample, the giant bucket might also be 20%. But is it possible that the giant bucket is 22% blue?
Yes.
Certainly, that sounds reasonable. Okay, 18% blue?
Yes.
Okay, 24% blue.
Maybe.
26% blue? Okay, so, all right, well, thank you for your participation here. That's definitely adding to the class here, okay? So yeah, you know, as the farther and farther we get away from 20%, we're a little bit more hesitant on, is this a reasonable number or not, okay? So intuitively, we got an idea behind this, okay? But we can't just go off of our intuition and say, 27% good, 28% bad, okay? We gotta back this up a little bit with our knowledge of statistics and probability, okay? And that's where our understanding of sampling distributions come in. Okay, so let me just recap everything that I wrote, or talked about just on the board here, okay? So, we're going to be talking about something called confidence intervals. So we don't know what proportion exists in the population. So we take a random sample, and based on this random sample, we will try to make a range of plausible values. For the population proportion. So I take a sample, this is random sample. So my p hat is 20%. And based on this, we got to come up with reasonable values of what proportion could exist in the P. Okay? And again, we have no idea if P hat 20%, if that's more or less than what's the proportion in the population. Okay. All right, is everybody with me okay on just the concept that we're trying to approach here? Okay, and so I want to just take a moment and just say, we're going to see this concept of confidence intervals a few more times, okay? We're going to see confidence intervals for a single proportion. We're going to see confidence intervals for a difference of proportions. Oh no, not for difference proportions. We're going to see confidence intervals for next week for means, and then a difference in means. And they feel different, but they're all the same. Okay, at the base of everything, the concept behind it all is the same. Okay, it's just like switching from driving a sedan to driving a truck. Okay, maybe the control for drive and reverse and stuff is now on the steering column rather than in the center console and things. Things might have changed around, but the overall concept is the same. But it's easy to get lost in the formulas for everything, and I don't want that. Okay, so what are reasonable values for P, the proportion in the population? Okay, all right. So just intuitively, maybe 17% to 23%. Does that sound reasonable? I don't know. What about 15%? Who thinks 15% is reasonable? Okay, a few of you. Unreasonable, 15%? Okay. But if 15% is reasonable, then 25% should also be reasonable, right? Because right now 20%, this is what I observed, and so, well, we're expecting the population proportion to be somewhat close to 20%. So maybe 15 to 25%. Who knows? Okay. So basically, I'm just doing 20% plus or minus some, either 3% or 5% or something. Okay. So let's use what we know about sampling distributions. Okay. According to Chapter 7, okay, or from what we learned in Chapter 7, we know that whenever I draw a random P hat, this comes from a normal distribution, right? And what's the center of this normal distribution?
The mean.
Okay, not the mean, but what?
I was going to say the mean.
Portion of
The population proportion. That's the center, or that's the mean of this normal distribution, okay? And we learn things like, anytime you take something out of the normal distribution, 95% of the time, how far is this number going to be from the mean?
1 standard deviation.
Within 2 standard deviations, okay? Or 68% of the time it will be within 1 standard deviation, okay? And if I said 90% of the time it'll be within, you guys know 1.645? Does that sound familiar? Okay. Well, okay, so then based on this, so we'll just deal with 68% of the time it's going to be within 1 standard deviation, and 95% of the time it's within 2 standard deviations of the mean, which is our population proportion. Okay. So when I see P hat is 20%, I can say I'm 95% confident that this number is within 2 standard deviations of the population proportion. Yeah? It might be more than 2 standard deviations away, but I'm counting on the fact that 95% of the time, this number is going to be with, or not this particular number, that any p hat that I get is going to be within 2 standard deviations of p. Or I could say I'm 68% confident that this thing is within 1 standard deviation of p. Is that train of thought okay? So, based on our understanding of sampling distributions, I can say I am 95% confident that the p hat I observed is within, and it's technically not 2, it's 1.96. Do we know this?
Yeah.
Okay. Within 1.96 standard deviations of the population proportion. And technically this standard deviation, what is the standard deviation? That's the standard error, okay? Where the standard deviation is equal to the square root of p times 1 minus p over n, okay? Standard deviation is equal to, well, I'm just going to write the standard error. And we've got to fudge the numbers a little bit, okay, for it to work. So if I know my standard error is, let's say, 2%, I can say something like a reasonable range would be 2% times 1.96, so about 4%. I'm 95% confident that P is between 16% and 24%. Okay, we'll write all of this out. Right now, p hat is my best guess or estimate for p. But it might not be exactly p, and so we're going to create a range. So my confidence interval will go from p hat minus what we call the margin of error, to p hat plus the margin of error. So maybe if my margin of error is 4%, then my confidence interval goes from 16% to 24%. Good? Any questions on this? Yes?
What's the difference between confidence interval and standard deviation?
Are you the standard error, or the standard deviation, or the sorry? What's the difference between a confidence interval and the standard deviation?
Yeah.
Okay, so the standard deviation is a measure of the spread on the distribution. Okay, and the confidence interval is something totally different. and it's a range of plausible values for, in this case, P, the population proportion.
Okay.
Okay? So the standard deviation is a single number. The confidence interval is a range of numbers. Okay? And so, so my confidence interval here, because I just made up this margin of error 4%. So how do we actually figure out a good margin of error? Well, because what we understand about sampling distributions, we can say, if I want to be 95% confident, how big should my margin of error be? Two standard errors. Okay, my margin of error should be actually 1.96 times the standard error. Does that make sense? If I want to be 68% confident, how big should my margin of error be? Roughly one standard error, okay? If I wanted to be 90% confident, how big should my margin of error be?
1.64.
Yeah, 1.645 times the standard error, okay? So there's actually, so this number comes from there, and so other confidence levels, so if you wanted to be 80% confident, you would pick 1.28 times your standard error. If you want to be 90% confident, you'd pick 1.645. 95% confident, 1.96. And if you want to be 99% confident, you would pick 2.58. If I want to be 100% confident about where P is, what would I have to do?
4?
Not 4. If I want to be 100% confident about whatever proportion exists in the population, what's my confidence interval going to be?
0
0 to 100.
0 to 100%. Okay, if I want to be 100% confident about getting the true population proportion, all I have to do is say, okay, the population proportion is going to be somewhere between 0% and 100%. Okay? I'll money back guarantee on that. You know, like 100% confidence interval. Okay? But that's a little bit ridiculous, right? Yes.
Do we just know these numbers, or is there any way of calculating them?
You can look them up in the Z table, but just these you should just know or write down on your note sheet or something. Okay? These will be values that will appear. Okay. But 1.96, you guys should know that one. Okay. Maybe this one you should definitely know. The other ones, I would say these two, and then these two are optional. Okay. All right. So if I were to make a confidence interval, so a 95% confidence interval would look like this. I would put P hat in the middle, and I would go plus or minus the margin of error, which we established was 1.96 times the standard error. Okay? So I just combined from the low end to the high end into one thing with a plus or minus. Alright, and so the standard error is normally the square root of P times 1 minus P over N. Okay? We don't know P. P is the proportion in the population, and we're making a confidence interval to figure out what P is, so that we don't know what P is. So we're just going to do our best guess. So we're fudging the numbers a little bit, and we're just going to use P hat rather than P. Okay? So just use this as our standard error. Standard error for a confidence interval. point out that these values here, these are known as critical values, okay? And we will see confidence intervals again and again and again, okay? And they're all kind of in this form, but rather than p hat, we use other values and things like that. All right, so let's say somebody tampered with my bucket of M&Ms or giant vat of M&Ms, and so I got upset and I said, oh, I gotta figure out what proportion is blue. So I drew 100 M&Ms out, 20 are blue. Let's make a 95% confidence interval for the proportion that is blue in the population, or in the bucket for that. Okay, so go ahead and do that. You guys should be able to do this in a couple of minutes. That's my sample size. So I don't know the size of the population, but I do know my sample size.
Oh, okay. That's all right.
So this is my sample size. All right, who's done? So what you got? Good job. All right. Okay, so that's your answer. 0.1216 to 0.2784. All right. It's this is our formula right here. P hat 0.20 plus or minus 1.96 times my standard error, which is the square root of 0.2 times 1 minus 0.2 or 0.8 divided by 100. So I get 0.20 plus or minus 1.96 times 0.04. And so I have 0.20 plus or minus 0.0784. So basically, I'm going from 12% to 28%. These are plausible values for the proportion that's blue in my giant bucket of M&Ms, okay? So when we were making up estimates here, we were being kind of conservative when we were saying, oh, you know, 15 to 25%, that seems a little bit unreasonable. But truly, reasonable values are actually between 12% and 28% blue M&Ms when your sample size is only 100, okay? All right, is this okay? All right, so our interpretation here, okay, and this is the important part. So you gotta know how to calculate the confidence interval, but you also have to understand what it means. Okay, so if this is my 95% confidence interval, I would say I am 95% confident that P, which is the proportion of blue M&Ms in this instant, between 12%, or basically 0.1216 and 0.2784. Yes?
So on test examples, whatever, you want us to give our final answer in a sentence form?
Okay, so I'll probably ask, what's the confidence interval? And then I'll say, complete this sentence. I am 95% confident, what? That P, the proportion of blue M&Ms, is between 12, this is proportion of blue M&Ms in the population. I get it. Sorry, let me, blue M&Ms in the population. Is between 0.1216 and 2784, 28%. So if I asked, is this evidence that the proportion, okay, so you pull out 100 M&Ms and 20% are blue, and I say, is this evidence that my proportion in the bucket is not 26%? What's your answer? No, it's not. Okay, so is this evidence that the proportion in the giant bucket is not 26%? The answer is no. Why? Yeah, because 26% is within the confidence interval. But if I say, is this evidence that the proportion is not 10%? What's your answer?
Yes.
Yes, because 10% is outside of the confidence interval. If I were to make a 90% confidence interval using the same exact data, how would my confidence interval compare? It'd be a little bit narrower, right? It wouldn't go from 12% to 28%. It would go from about 13.5% to 26.5%. Okay, so we get a narrower range, and that would be. But the trade-off is, okay, is that I can give you a more narrow range. Because let's say I tell you something, I'm like, okay, well, the proportion that's blue in the bucket, I'm 95% confident that it's between 12% and 28%. And I'm like, 12% to 28%, that's such a huge range. This is useless to me. Okay? Can you give me something a little bit more narrow? And you're like, sure. Okay? And you can make a confidence interval that's more narrow, but you're now less confident about it. Okay? So that's the trade-off. It's just like, you know, if somebody escapes from prison and they go on a fugitive manhunt, all right, and they say, you know, how big of a zone should we blockade so we can search the area? You can say, oh, well, just block off the entire city. I'm sure the prisoner's somewhere in there. And you're like, no, that's too big. Okay, we'll never be able to search that area. And I say, okay, well, we can shrink the area, but now I'm not so sure that the fugitive is somewhere in this region, right? Okay. So that's what we can do. We can always be more confident by making a wider interval, but if you need a smaller interval, you got to you're trading off some level of confidence there. Okay, so also keep that in mind. More higher confidence means wider intervals, lower confidence, narrower intervals. Requires wider intervals. Okay, and then narrower intervals. Can be found with lower confidence levels. Okay, that's what I got on confidence intervals. Okay, so I'm gonna move on. So one way we can look at a proportion is using confidence intervals, and the other way that we can do some inference about the population is doing something called a hypothesis test. Okay.
This gives us different perspectives on how to look at the proportion.
No, I mean, I don't know. It's a different approach here. Okay. So with the confidence interval, we said, okay, I have no idea what's in this population, but I'm going to draw out a little bowl of a sample here, and based on what I see in the sample, I'm going to create a range of plausible values for the proportion that exists in the population. That was a confidence interval. With a hypothesis test, again, we don't truly know what exists in the population, but we want to test to see if a certain value is possible. If a certain value is possible, okay? So in the story with the M&Ms, okay, so let's say they apologize for changing up my vat of blue M&Ms or a vat of M&Ms, and they say, okay, all right, Mr. Chen, we're sorry. Here's a new giant bucket of M&Ms, and just as you requested, 15% are blue. Okay, and I'm like, I don't know if I trust you guys, right? I don't know if I trust you guys. How do I know that 15% truly are blue? Okay, well, they say, okay, well, go ahead and draw out a random sample. So I go and I get my scoop of scoop, and I pull out some M&Ms and I dump them out, and let's say I counted up 200 M&Ms and only 12% were blue. I said, what's going on here? You told me 15% are blue, but I just pulled out 200 M&Ms and 24 are blue. That's only 12% blue. Are you trying to cheat me out of my blue M&Ms? And they're like, no, I promise, okay? So this is, I mean, that's a ridiculous story, but it gives an idea of how the hypothesis test works, okay? So someone has told me that in the bucket, in the giant vat, is 15%, okay? But I just pulled out a sample and I only got 12%. So are they lying to me, or could I get 12% just by the fact that it's a random draw of M&Ms? Okay? So you guys are kind of nodding your head and you're saying, oh, well, 12% doesn't seem so far away from 15%. So, you know, just because it's a random draw, maybe you just got a little bit unlucky and got 12%. Okay. But what if I reached in there and I drew out only 10% blue M&Ms out of a sample of 200? Then is that too much, or is that too little? I don't know. Okay, so this is where we're going to do a hypothesis test. So let's. So again, so I'm given a bowl, or given a bucket of M&Ms. I don't know the proportion. proportion that is blue. But they tell me it's, someone says it's 15%, but I want to test that. Okay, so I draw a random sample of 200 M&Ms. And I get, let's say, only 10% blue. Okay. Does this mean the proportion in the bucket is actually less than 15%? That's what we're asking here. Okay. So does the question setup make sense to everybody? These silly scenarios here. Okay. Well, what can we do? So what I'm going to do is I'm going to say, you know what? I'm not going to call you a liar. I'm going to give you the benefit of the doubt. Okay? Let's say what you're telling me is true. Let's say the bucket truly is 15% blue M&Ms. Okay? If it truly is 15% blue M&Ms, then what is the probability that I draw a sample of 200 M&Ms and get only 10% blue? Can we figure that out? Can we solve that problem? We can, because we learned how to do it in chapter 7. So I'm going to say, okay, let's assume you are telling the truth. Let's say the bucket really is 15% blue M&Ms. Okay. So let's figure out, maybe I did just get unlucky and get only 10% in my sample of 200. Well, let's figure out what the probability is. Okay? Then what is the probability that I draw
Spider.
Oh, poor spider guy. He's trying to make a living here, you know? Does this line of thinking make sense? Alright, so let's say we go through the math. We haven't done it yet. But if this probability is high, so let's say it turns out there's a 25% chance of drawing 200 M&Ms and getting 10% blue, if the proportion truly is 15%. Then what would we say? So let's say this turns out to be 25%. What would you say?
There's a 25% chance of drawing 20 M&Ms out of 200?
Yeah, we'll say 20 or fewer, right? Because I'm saying, you know, does this, you know, I'm asking, So I only saw 10% blue M&Ms, and I'm like, are you cheating me out of my blue M&Ms? Are you giving me actually fewer blue M&Ms than I wanted? I requested 15. I specifically requested 15%, and I'm pulling out a sample and I'm only getting 10%. Okay? So I'm asking, what's the probability that I draw a random sample of 200 and see only 10% blue M&Ms? You know, if I give you the benefit of the doubt. Okay. So let's say this answer turns out to be 25%. Then what I say, I've got a 25% chance of what? Of getting 10% blue M&Ms. So does that seem like a high percentage or a low percentage or what? It seems kind of high, right?
Yeah.
It seems like, you know, 1 out of 25% means that anytime somebody reaches in this bucket and pulls out 200 M&Ms, 1 out of 4 times, they're only going to get 10% or less. They're only going to get 10% or less. So very well, I could have just been one of those unlucky 25% that got a sample with fewer M&Ms. But let's say we did the math and it turned out to be 1%. That the probability of getting 200 M&Ms and seeing only 10% blue M&Ms is only 1%. Then what would you say?
That you got cheated.
That I got cheated, right? Okay? So I do the math and it says, okay, just imagine the scenario here, right? So over here, I'm selling the, I'm bringing back the crate here, and I said, look, I got you a bucket of M&Ms, and 15% of the M&Ms are blue. Alright? Just trust me on this. I said, I don't know if I trust you, right? I'm going to pull out some M&Ms and test it myself. So I pulled out a bucket of a bowl of 200. I count them up. I go, look, there's only 20 blue M&Ms here. There's only 10% of my sample is blue. And you told me that there should be 15% blue M&Ms. So I'm like, oh man, I don't know what happened. You just got unlucky, alright? You just happened to draw a bowl of blue M&Ms and just happened to get fewer M&Ms, fewer blue ones than you should. Okay? So, okay, well, alright. I know statistics, so let's test this out, okay? And so let's answer this, okay? So go ahead and do the math and see if you can do this, because you know how to do this. You learned this in chapter 7, so go ahead and take a moment and try to figure out what's the probability of seeing only 10% blue M&Ms or less. 10% or fewer or less blue. so I'm walking around and seems like a lot of you guys are a little bit lost, okay? So if we assume someone's telling the truth and the bucket truly is 15% M&Ms, okay? Or 15% blue, what does my sampling distribution look like? Meaning, what is the mean and standard deviation of this sampling distribution? What goes right here in the middle? 0.15. And what's the standard deviation? What do I put here? 0.15 times 1 minus 0.15 divided by 200, okay? This is my standard deviation because we are answering this question based on the assumption that 15% are blue, okay? And what am I looking for? I want to know what's the probability that I get 10% blue or less. Can we do this now? Okay, so give me an answer here.
0.025.
0.025, is it really?
Mm-hmm.
Yeah. Yeah.
Okay, yeah. Alright, so my standard deviation ends up being 0.0252. Okay, so my z-score well, we'll say standard error. Maybe 1.98. Z-score is negative 1.98. Is this? Are we getting that? Okay. And so we look this up in our z-table and we get 0.025 or something like that. .0239. So we say, so 0.0239, that's the answer to this question. What is the probability that I draw a random sample of 200 M&Ms and see only 10% or less blue? And the answer is 0.0239. So right now, you have a choice, okay? Oh, okay, so I'm the guy trying to say the bucket's okay. I'm saying, oh, the bucket is actually 15% blue M&Ms, and you are just one of the unlucky 2% of people that takes a sample of 200 and gets only 10% blue M&Ms. Okay, that happens 2% of the time. So you were just one of the unlucky 2%. Do you buy that? Or do you think, I think you're cheating me? What do you say?
I buy it.
You'd buy it? Huh? Okay, so well, it depends what's on the line. But I would say, if someone's saying there's a 2% chance, there's only a 2% chance, so the probability of me getting a random sample where I'm only getting 10%, if that's only 2%, I would say, you know what, I'm probably not one of the unlucky 2%. Probably what's the problem is not me. It's probably not me that, there's a 2% chance that it's me, just being unlucky. But I think the bucket is not really 15% blue M&Ms, okay? So because this probability is low, so I reject, the assumption that 15% of the bucket blue M&Ms. Who's confused by all of this? Yes?
A little bit confused.
Huh?
A little bit confused.
Okay, what part is confusing?
I guess just the z-score part. I was fine doing the standard deviation until we had to do the z-score.
Okay, so how do you find a z-score?
Well, what I'm saying is that what's the importance of the 0.0252 to the z-score?
Wait, my z-score is not 0.0252. This is my standard error.
Yeah, I'm sorry, that's what I meant.
Okay?
So then we're gonna put that at the bottom, divided into.
Yes, so I want to know how many standard errors, or the z-score is how many standard deviations you are from the mean, right? So here I am, I'm at 0.10 and the mean is 0.15, and each standard error is 0.0252. So if I do this distance of 0.05, basically I'm 5 percentage points away from the mean. If I divide that by each standard error, which is about 2.5 percentage points, then that tells me I'm about 2 standard errors, okay? So this is, so, did chapter 7 go okay for you?
Okay.
Is it alright? Okay, so this is basically, we're applying what we learned in chapter 7 to kind of this new situation here, alright? And so, I get, my question is, do you understand what 0.0239 means?
Yeah.
Okay, so.
That's the area, the shaded in area.
Okay, so tell me, okay, yeah, that's the shaded in area, but why is this shaded in area of 0.0239 important?
Why is it important?
Yeah. Can you tell me,
Is it that the probability
okay, it's the probability of what?
of, if you were to pull out 10%, or if you were to pull out 200, that 10% of blue, is that what we're doing?
Okay, so it's the probability of taking a sample of 200 M&Ms and getting only 10% blue M&Ms, okay? It's the probability of that happening if what?
If it's 10%.
If what is what?
Okay, now.
Okay.
You know.
No, that's okay. It's a tough concept, all right? And I'm sorry, I'm not trying to put you on the spot and make you feel better or anything like that. But and I don't know if the other students are.
The original one, sorry, the original was 15%.
Yes, exactly. Okay, so it's the probability of taking a random sample of 200 M&Ms and getting only 10% blue M&Ms if the original population truly is 15% blue. Okay, so if this population really is 15% blue, you know, it's possible that anytime I take a random sample, I don't get exactly 15%. What's the probability that I get 10%? That probability is only basically 0.0239. Okay, the probability of that is pretty low. So rather than saying I was one of the unlucky 2% that it happens to, I'm going to say maybe my initial assumption about the population is wrong. Yeah.
How can you just make that assumption?
Which assumption?
Assumption that the original 15% is too large.
Because this probability is only 2%, right? Okay, so let's say I do if I show you a deck of cards, okay, and I say draw out a card, and you draw one, and then I say I'm gonna guess what it is, and what if I got it right? Say 7 of clubs. How'd you know that? Okay. Truly, I could have just been lucky, right? Do you think I was lucky, or do you think I actually did something to figure out what your card was? I probably figured it out, right? I could have been lucky. I could have just said 7 of clubs and happened to be lucky, because I got about a 2% chance of being right? 1 in 52. It's a little bit less than 2%. So you could, you could always go to a magic show and always be unimpressed and just say, you just got lucky, man. He's just really lucky. Just 2% chance every time of getting the card right. I'm not impressed, okay? But most people are impressed because we say, oh, You did something to figure this out, okay? And that's basically what's happening here. It could have been, I could have just been, quote, lucky or unlucky, because it happens about 2% of the time. But rather than saying, maybe I was one of that lucky or unlucky 2%, I'm going to say, probably, my initial assumptions about the situation were not correct. Okay? I want to make sure that line of thinking is okay. Alright, so, while it's, this process is still kind of set in our minds, let me just lay out the formal steps of a hypothesis test, okay? Yes? You have a question?
So, is it truly 50% then if we reject the...
No, what we're going to say is, I reject the assumption that 15% of the bucket is blue, okay? So I'm going to say it's probably not 15%, it's actually probably something less than 15%. I don't know what it is, but if it were 15%, it's very unlikely that I would have gotten only 10% blue in a random sample. So I'm going to reject that idea. Yeah?
So if the question was very similar, except that it was NBC at least 10% more blue, would we solve the problem the same, except we just subtract the final Z-score from 1?
That would never happen in a situation like that. Okay, you would have to go. We'll talk about this. Okay. That's a good question. Okay, so let's just do hypothesis tests and the formal steps here. Okay. So the first step is to create your hypotheses. So you have something called the null hypothesis, which is H0, and the alternative hypothesis, which is HA. Now, what was it that we were trying to test? We wanted to know if my bucket of M&Ms was truly, what, 15% blue or not, okay? So how can I write that statement symbolically with hypotheses? So my null hypothesis is that the proportion that's blue is 0.15, okay? So I'm going to say P, which is the population proportion that's blue, is 0.15. And then, if that's not correct, then the alternative must be that my proportion was actually less than 15%. Well, not according to the setup of our problem. We're testing to see if it's less than. Okay, if they gave me more than 15% blue M&Ms, I guess that's okay. But I'd be upset if they gave me less than 15% blue because something. Yes.
The A stands for alternative.
The alternative. Yes. So this is known as the null hypothesis, and this is the alternative hypothesis.
And that's the symbol.
H0 and HA.
Where does the slash do that come in?
The slash?
Yeah,
P
the
is
slash.
less than 0.15.
No, like in the book it says P and then the equal sign. It has
Oh,
a
not
slash
equal.
over it. It has a slash over the equal sign if it's.
Yeah, that'll be a not equal to. Okay. So other the alternative could also be P not equal to 15% or P greater than 15%, depending on the situation. Okay, depending on the problem. Okay, so if this was some other situation, says, oh, here's a box of toys from my factory. Okay, I promise no more than 1% is going to be defective, and then you go through and you take out, 1,000 toys and you test them, and it turns out that maybe 15 of them were defective, so you got 1.5%. So in this case, you want to know, is it really equal only to 1% defective, or is the proportion defective greater than 1%? So it depends on the situation. Okay? So we create the hypotheses, and then the next part is we have to figure out a test statistic and the p-value. Okay? So basically the p-value is the probability of observing your data or something more extreme if you assume that the null hypothesis were true. And that's what we did. We said, let's assume that the null hypothesis were true. Let's assume that the proportion in the bucket truly was 15% blue M&Ms. Then what is the probability that I would get a random sample where only 10% is blue? Okay, and this builds off of our understanding of Chapter 7 and sampling distributions. So our test statistic is our z-score. And in that case, we figure out p hat minus 15%. This is the proportion from our null hypothesis divided by the standard error. And the standard error or generically it's p times 1 minus p divided by n, okay? And here we are using the p from the null hypothesis. So once we get the test statistic, we look this up in our z-table to figure out the probability in the tail. Okay. So the p-value is basically you look up your test statistic in the z-table. Okay. Whether or not you look for the area to the left or the area to the right depends on the alternative hypothesis, okay? So if the alternative hypothesis has less than sign, okay, look for the area to the left. If the alternative has greater than sign, we look for the area to the right. To the right of the test statistic. Of the z-score test statistic. Okay, and if the alternative has a not equal to sign, look for the area in the tail and then multiply it by 2.
What is the tail?
Okay. So tail is this. Okay. So let me just clear out a little space here. So this is your normal distribution, right? So if my z-score is positive and it's over here, then the tail is basically the triangular piece. Okay, so whichever side does not contain the hill is going to be the tail. So I look for the area in the tail and then I multiply it by 2. Okay, but for all of the other problems, if it's if it's over here and you got p, the alternative has a less than sign, then you're going to go for the area to the left. If we had a greater than sign, then you go for the area to the right. If it's not equal to, you take the area in the tail and you multiply it by 2. Alright, is that feeling okay? Yeah? No? Alright, let's take a short break and then and we'll come back and we'll finish the class.